Hello, we are Group AEZ1, and our project is Autonomous Fleet Collaboration for Unknown Territory Exploration. Now, throughout history, from the great minds of Euclid and ancient Rome creating the lens, all the way to Hans Lippershey creating the telescope, technology's evolution has always driven humans to look up into the stars and has always driven astronomy and exploration. Now, advancements in autonomous aviation and drones can even be dated back all the way to World War I, and these have now expanded into the consumer and research fields. However, certain limitations in aerospace optics, communication technologies, and particularly navigation have prompted a need for innovative solutions, and that's where we come in. Our project proposes using cameras, coding algorithms, and a combination of air and ground vehicles to overcome navigational challenges. Inspired by the movie WALL-E, it aims to transport a plant aligning with the environmental themes of the modern tech's potential for ecological progress. This project is rooted in addressing navigational limitations and environmental issues. We focus on leveraging hardware knowledge and coding practices, utilizing a Raspberry Pi and Arduino to enable communication and image analysis. The main scope of the project is to have a drone autonomously fly over a designated area. Using a Raspberry Pi to control the drone and a Raspberry Pi camera to map out this previously unexplored area, the drone will detect the rovers, it will detect the resource, in this case water, and it will detect any obstacles placed in the rover's path. The obstacles are in place to prevent a linear path between the rovers and the resource. One plant will be placed on top of each rover. The point is to get the rovers to the resource, water, without crashing into each other or crashing into any of the obstacles. This will be done by the Raspberry Pi camera mapping out the shortest possible path for each drone, which will be communicated to the rovers via a Wi-Fi module. The rovers themselves will be controlled by Arduinos, and these Arduinos will let the rovers drive themselves, not deviating from the previously given path of the drone to the resource to deliver the plants to their much needed water.
In this project, our focus is solely on building and adjusting the physical hardware of the drone and a minimum of 2 rovers. The coding aspect involves utilizing hardware components like Wi-Fi modules, Raspberry Pi and Arduino on both the drone and the rovers. The initial designs for both vehicles have been established and constructed as shown in the original design here. The rover features a metal chassis with 3 wheels, each equipped with smaller wheels moving perpendicularly, allowing omnidirectional movement for easy obstacle avoidance, which is one of the pros here. However, this design comes with a cost of maneuverability on rough terrain, an important aspect we aim to test in outdoor settings. Additionally, this design may lack stability for heavier payloads. This new design, constructed on CAD, keeping the original design for the drone, employs the use of tracks for better maneuverability, but with the cost of being able to sense obstacles and move in any direction at any given time. It also allows for better weight management. Because of the short amount of time for this project and the effort that we must put into the coding, the original physical design was picked, but left the possibility for multiple functions of the system itself, including one where the drone is the sole navigator for the rovers, and one where the drone still does the same job, but with the rovers now having additional sensors to help with object detection. This second choice was used, as the cost was very small compared to what there is to gain.
The final design chosen was one with sensors placed both on the drone and on the rover, using the original design for both. While this design is feasible, it does have a few drawbacks because of the increased weight of the aluminum base for the rover. It has an increased power requirement than a lighter composite base. The wheels chosen for the rover also offer poor traction on rough terrain. Both of these issues can be addressed at a later date with a new composite platform and a more aggressive tire. This would also allow for wire management of the rovers, as the current products leave little room for sensor placement. In all, this design is feasible and only requires minimal adjustments for optimization.
So one key component is for the drone to tell where the rover is to go. So we'll be following these steps. First, we take pictures from the drone. Second, segment them so we know where the obstacles are. Then we run the pathfinding algorithm, and every set amount of time we will repeat this. So here we segment the image by using the OpenCV library. From the images, we can see that there are random objects on the ground, and the drone should know that the rover cannot traverse those. So by using different techniques, we can make it so the background is white and all the obstacles are fully black. So once we know where the obstacles are, we use the randomly traversing random trees algorithm on the empty white space to find a path. And as shown in the image, we have an output path starting at the start at 0, 0 to the destination marked by an X that goes around the obstacles. And using that path, which is made of coordinate nodes, we can output them as a direction and a distance so that the rover can follow. So given all these, we can have a drone take an image as input and send a list of directions and distances to the rovers.
The movements of the rovers will be dictated by the inverse kinematic equations shown here. The angular velocities of the motors are a much safer independent variable to work with rather than the total velocity of the rover due to the mechanical inconsistencies present in the motors. By using an Arduino Mega microcontroller, the rover can adjust these values on its own by taking the path drawn by the drone as reference. The equations of motion for the drone are a bit more complex, but by simplifying the shape of the drone to two intersecting thin rods, it is possible to derive equations for the angular velocities of all four motors. Since the drone will only fly in a single direction and then hover, it is unnecessary to consider other velocity components. Once again, we selected the angular velocities of the motors as the independent variables to ensure better control over the system. We selected a Raspberry Pi computer as our drone's brain, since the drone's responsibilities are computationally more demanding. By utilizing the previously mentioned equations and a controller, we can roughly simulate the expected path our drone will take as it tries to hover at a set altitude. As seen here, the drone eventually settles at approximately 5 meters above the ground.
This semester, our primary focus was on testing the existing drone functionality in order to determine what we would need to work on moving forward. Initial testing took longer than anticipated due to compatibility issues with the existing hardware, and we ended up having to replace some parts. However, once the testing phase was complete, we began working on component specifics, such as autonomous flight and object detection functionality. Ultimately, our plan for the next semester is to have each component finished before putting it all together. Ideally, this would be completed as early as possible in order to allow for adequate time for testing. We utilized a Gantt chart in order to monitor the group's tasks and stay on track, which we divided into two separate groups for the rover and drone. Thank you.